Okay, so we got to this point in our analysis of this reaction, and one thing maybe we'd like to look at is how does the extent of reaction at equilibrium, how does that depend on pressure? Because Kp doesn't change, but Xi does, right? The extent of the reaction does change to keep Kp constant. One thing I'll just emphasize here is that Kp can change with temperature. That's based on the equation, right, that we had previously between delta G. There's a temperature dependence in there. There's not a pressure dependence, though. And we will look in future video at how equilibrium constants do change with temperature using the Van 't Hoff equation. But we'll get to that. Anyway, in this video, we're interested in how does this extent of reaction depend on P, and we'll actually look at a plot of this as well. So we have an equation that relates Kp and pressure and Xi. So we'd like to just solve this equation we want to solve for the extent of reaction at equilibrium. Okay, so we can get, first step is pretty straightforward, divide Kp by P, so we can, get rid of that pressure on the right-hand side. All right, so we have 1 minus I squared. I'm probably, after this, I'm just going to drop writing the equilibrium. Just remember that this is at equilibrium. Okay, so we need to then now multiply Kp over P times 1 minus Xi squared is equal to Xi squared. Okay. Now we need to distribute this, so we have Kp over P minus Kp over P times Xi squared is equal to Xi squared. All right, and now we can go ahead and add our term on the right. Kp over P is equal to Xi squared plus Kp over P Xi squared. Now we can go ahead and factor out the Xi squared. My screen's not, there we go. So this is equal to Xi squared times 1 plus Kp over P. And we're almost there. Xi squared is equal to Kp over P divided by 1 plus Kp over P. And so, I'll put the equilibrium back in here. Xi at equilibrium as a function of pressure is equal to Kp over P divided by 1 plus Kp over P, all that raised to the 1/2 power. Okay, so that gives us an expression. And we can go ahead and, using a known value for Kp, right, this is a constant. So Kp, we can look this up, is equal to 5.4. This is some information from your textbook, at a particular temperature of 200 degrees Celsius. So at 200 degrees Celsius, this reaction will slightly favor decomposition, at this temperature. Now, let's go ahead and look at, we can plot this equation here and have this as our x-axis. Sorry, no, that's our y-axis. We want to plot. This is our dependent variable. Have this as our y-axis and P as the x-axis. So we can look at, as pressure changes, how does this extent of reaction change? And let me go ahead and pull up that plot. Got to copy and paste it over here real quick. I think if I take this out of full screen, then it'll actually work. Okay, so we can see here we have our y-axis is our extent of reaction at equilibrium, right? And this is in units of moles. And we have our pressure down here in bar. So at very low pressures, at 0 bar, the reaction goes to completion, right? We have a Xi equal to 1. So at the theoretical 0 bar value, right, where there's no pressure, the reaction will completely favor dissociation into the products. So that's what this means. Up here we have PCl5 completely dissociates. Now then, as the pressure increases, we have this dependence of the extent of reaction on pressure, right? To maintain the value of Kp equal to 5.4, right? That stays the same no matter what. All of this is at 200 degrees Celsius. Because we're changing the amount of moles, right? Our total number of moles is changing. That means the equilibrium has to shift to be able to maintain this value of 5.4. So as we keep increasing the pressure, this is Le Chatelier's principle in action. As the pressure keeps increasing, our equilibrium shifts more and more to the left, meaning that our extent of reaction decreases. So as we get to, say, somewhere between 20 and 30 bar here, at this point, xi is only equal to 0.5, approximately. Which means that now only half of our PCl5 has dissociated. Half of it remains associated as PCl5, and half of it completely dissociates to Cl2. Half of it dissociates to Cl2 and PCl3. And then as the pressure keeps increasing, that keeps going further and further until at 200 bar only about 20% of the PCl5 actually dissociates. The other 80% remains associated. And so we can see here we have Le Chatelier's principle in action. We can actually quantitatively state how much is going to dissociate instead of qualitatively, like probably you're used to in general chemistry. So that's an example of the sort of analysis we can do with this idea of extent of reaction and with the tools that we have in terms of equilibrium constants. You'll get a chance to practice this in class and also on some homework questions with some other types of reactions. Not necessarily this particular reaction, but similar things, looking at things in the gas phase.